Hi, my name is Bill Fortney, and thanks for being here as we're doing probability and statistics and looking at the real world aspects. And this is the last one in kind of the foundation series for real world. And we're looking at the idea that measurement is really hard, and the aspect of that measurement is just an estimate. Okay, so we've looked at there's variation in everything. We've seen what to do with that. The thing you're measuring, the population might not be stable. What to do with that? Now we're focusing on the fact that your measurements are only an estimate. So when we measure, we use a measuring system. There's some actual value. It's going to go into our measurement system, and out the other side is going to be our estimate of the actual. You've seen already in the reading that you've done that our measurement is only a estimate of the actual value. And the difference between the two is our measurement error. And inside the measurement system is our device. So like if we're checking the strength of these, we got our tensile tester, but then also the operator, also the procedures that an operator is using, also the conditions that things were done under. All of those things are part of our measurement system, and they're part of this actual value being transformed into a measured value. Okay, a couple of realities. Number one, we've already said this, but a measurement system is always just an estimate of the value of the real thing, the characteristic being measured. The quality of that estimate is going to depend upon you and how well you design every bit of this measurement system. You remember the question from our manager: do the measurements estimate the true values well enough for the decision being made? That's what he's talking about. And you remember in Nathan's lecture, he was going through some measurement terms. He talked about resolution. He talked about dynamic response. All those things are part of designing your measurement system so you can tell your boss yes. So let's say, for instance, you were measuring something that's changing, and it's changing 5 times a second, and you're trying to measure that. And the device that you picked has a dynamic response of 2 times a minute. Well, you can't get there from here. Your thing is changing 5, you can only measure 2. Your measurement system is not going to estimate the true value. That's what this is talking about. And you will learn how to design your measurement system so that it does. But it's really important. Okay, another reality is measurement systems have variability. Every one of these components can add variability, error, to your estimate. And the output, this measured value down here, is a random variable. And if you never thought of it, that might be a little bit of shock because you're thinking random variable. Well, wait a minute. Random variables can be anything in the range. That means I could measure the exact same thing 5 times and get 5 different numbers. Yeah, that's exactly what that means. That's what I want you to realize about measuring. It's hard. So let's jump back. You remember we used this, we measured, had 5 different measuring devices. We use this as an example for changing the channel. I want to come back to it now and look at what this is telling us. Here's method 1, method 2. Okay, method 3, 4, 5. Remember I told you before, those, they're not calibrated. I'm not even going to pay attention to those. But just looking at method 1 and 2, I see here there's a lot more variability here. No, but wait a minute. I was measuring a gauge block. Every single time I measured, the block did not change. Remember, is our process stable? Yeah, our process is stable. It's a block. And it is a gauge block that was 10.000. So I don't have to worry about I measured in different spots or nothing else. It is 10.000. So the fact that these are jumping around is entirely variability in my measurement system. Whoa. So let's understand that a little bit. So first, forget that they're measurement devices. These, I'm plotting bolts from our factory that are normally distributed. Okay, forget that they're measurement devices. They're just on plotting bolts like we always have. So what do we know? Well, we know what I can expect. Whether we want 99 or 95% certainty, I can put a range on here, that's 95. And I know that my values are going to fall within there. Not only that, I also know that I can get any value in this range. Okay, I know that. Now, let's go back that method one really is a measuring device. Lots of measuring devices do follow normal or at least symmetric processes. So what that's saying is, if I'm measuring this 10-inch block, when I measure it, I could get any of these values. Yeah, that is exactly what that means. You might get a 10, you might get a, depending, let's just do 95% certainty, you might get a 10.5 or you might get a 9.5. Anywhere in there. Do you see how bad that is? Let's say now you're trying to make a block 10 inches. So you go and measure it, and it measures 10.5, and you think, oh crud, I'm a ½ inch too big. I need to go mill it down some more. You mill it down a ½ inch, you've just made it too small potentially. Does that make sense? That's why measurement is really a pain. And this band right here, that's the uncertainty. How uncertain am I? Well, plus or minus, if I'm 95%, ½ inch, my real value is going to be in there somewhere. So the measurements are random variables. We see that. I can get any value in the range. We've seen that. The measurement system has a standard deviation. Assume it's calibrated, so the average is 0 of 0.25. So then, if that's the case, our uncertainty, the uncertainty in measurement is going to be 0 plus or minus 0.5. There's no standard to this, but typically uncertainty is reported in 95%. So it's 2 times the standard deviation of the measurement system. That's one of the reasons why measurement is so complicated. It's because there's no standard for that. So when you read the uncertainty from a device, you don't know that it's 95%. You're kind of just assuming that. Okay, so uncertainty is what really matters to us. So let me highlight what that really means. Uncertainty refers to the doubt that exists in the measurement. Now, measurement error is exact. There is a certain amount of error. We never know what it is because we don't know the actual value unless we happen to be measuring a gauge block or something like that. Uncertainty is what we deal with and what we manage, and that reflects the doubt. How much doubt is there in our measurement? And the uncertainty gives a range of values within which the true value is expected to lie. We've been seeing this. It's like that plus or minus standard deviations. It's like the normal where we know that we're 95% sure the real thing is in there. That's what uncertainty is doing. So you have a measured value, and then the uncertainty tells you the true value is somewhere in that range X% of the time. So let me give you an example. Our device one, the uncertainty was plus or minus 0.5 inches at 95% confidence. So you go and measure 10.4 with that device. Here's what you know. You know 90% of the time, the real dimension is going to be somewhere between 9.9 and 10.9. That's what you know. Plus or minus 0.5 from what you measure. And let me just get your mind around that for a second. We're used to measuring something, getting 10.4 and thinking, hey, this thing I have is 10.4. No, it's not. You have uncertainty in any measurement system. All you know is that the true value is plus or minus the uncertainty of what you read. Let me show you how this plays out in real life. So I eat a bunch of Greek yogurt, so I make my own. And what you do is you take live culture and add it to heated milk. And the milk has to be 115 degrees Fahrenheit or below, or it's going to kill the culture. So you let it cool. Now, the uncertainty in my thermometer is plus or minus 2 degrees. So if I stick my thermometer in and it's 115, I understand that that could mean the real value is 117. It could be as low as 113, but it could also be as high as 117. If that was the case, I'd kill my culture. So what I do is I wait until the temperature reads 113. That way I know that the true value is going to be 115 or less, and I'm not going to kill the culture. You see, that is the reality of measurement with uncertainty. That value that you hold in your hand, even if you've taken 5 measurements and gotten an average, that's not the true reading. You have uncertainty added to that. And you're thinking, what? Yeah. You remember our example of the gauge block where we measured it and it was 10.5? It was really 10. It was just our measurement system had variability and we cut it too short. That is the reality of uncertainty. And so hopefully you're kind of thinking, what in the world? I mean, how do companies even operate? Well, here's how you deal with that. You look at the accuracy that you need for your decision. Like in our gauge block or the part that we were cutting, what's the tolerance on the part? Plus or minus what? And then what you do is you make sure you design your measurement system so that the uncertainty is way smaller than that. So that way you don't have to worry about the uncertainty. The uncertainty is not going to affect the decisions that you're trying to make. Now, how much smaller? You want it no more than a quarter of what the accuracy you need for your decision. A lot of people say you want it to be a tenth. So for instance, at NavAir, they use a quarter. So what that would mean is for me, let's say I realize, okay, if I'm 116 versus 115, it's okay. So I want to be plus or minus 1 degree is enough accuracy for my decision. Then what I would want is I would want a thermometer that read an accuracy of plus or minus a quarter of a degree. Does that make sense? That's what we're saying. If I wanted to be really, really, really precise or careful, I would want a thermometer that read 1/10 of a degree. So when you're designing your measurement system, that's what you're going to do. That's how you're going to get across the fact that there is uncertainty. And that uncertainty is a band, and all you know when you have a measurement is that the true thing is somewhere in that uncertainty. So you're going to want your uncertainty to be small, and you're going to need to pay attention to it. Okay, so what are we going to do? How do we deal with this? One, determining uncertainty of a measurement system is really complicated because there's variation in every one of these. And I don't know what happened to our little device block right there. And each one of them has to be estimated and included. Again, there's whole careers that focus on that. You're not going to do that. Here's my suggestion. A key component is the accuracy. A key component of the overall uncertainty is the accuracy of the device that you're using. And that's typically going to be expressed as a plus or minus number, like plus or minus 2 degrees, or a plus or minus percentage of the reading, so plus or minus 3% of the reading, or a plus or minus percentage of full scale. You'll often see FS. So my thermometer goes to 200 degrees, and it says plus or minus 1% FS. I would take 1% of 200. That's my plus or minus degrees, okay? That's what you're going to have on the accuracy of your device. The overall uncertainty can't be any better than the accuracy's device because it's a component in it. These other factors are only going to add more uncertainty because of inconsistency in the operator or the way you go about it. So my suggestion is, given your device is calibrated, the accuracy is the device's uncertainty. So use it as your uncertainty if you don't have any other information. You know your uncertainty is at least that much. So if you don't have any more uncertainty than these, at least use the accuracy of your device and call that your uncertainty. And remember, you need a device with uncertainty no more than a quarter or a tenth. Okay, so what do we do with all this? One, keep in mind that a measurement is just an estimate, so don't treat it like one number. Realize there's a band. Be aware of the uncertainty that you're using and make sure that it's appropriate for the decision that you're trying to make. And remember the level of uncertainty when you're drawing conclusions. Don't chase ghosts. And here's what I mean by that. You're trying to see whether two things are different or not. And the difference between them is less than the amount of uncertainty. That's chasing ghosts. There's no difference there. That's what I mean when I say be aware of the level of uncertainty when you're trying to draw conclusions. And then carefully consider the design of your measurement system up front to get that quarter or a tenth, and just be aware when you pick something up what its uncertainty is. Okay, so that brings us to all of the key pieces, the foundations we need for measurement. And we just hit the last one, the measurement. Carefully consider it and then remember the level of uncertainty. So you will use these as you design your experiment. You'll use them as you analyze data, remembering to be a detective. So good luck, and I look forward to seeing the results that you have when you start applying these to actual experiments to answer engineering questions.